tests. We're going to take a look at 100 subjects that are known to be sensitive to nickel. And we're going to go in knowing that in the general population, right, that that 20% of people are allergic to nickel. Okay, any of you guys allergic to nickel? I know I suspect I'm allergic to nickel. I suspect I'm allergic to nickel because when I wear tight watch bands, the stainless steel back on the watch. I think I might be giving you some feedback. Let me turn down the sound. The stainless steel band on the watch gives me a rash after a while if I sweat on it. Stainless steel, one of the components of stainless steel very often is, among other things like chromium and stuff like that, is nickel. And a lot of people are sensitive to it, more people than ever, because a lot of stainless steel a lot of stainless steel, what do you call it, piercings, have some nickel in them. And there's a kind of an increase in the prevalence of stainless steel allergies, stainless steel, or more specifically, nickel allergies. Okay, so some of you may have it, some of you may not, but it's something that's not rare. I made up a particular population that had 20%, a 20% prevalence of nickel allergy. Let me just go back to the notebook. There we go. Let me get my Galton machine out of the way and get a nice, clean, fresh page. And okay, so I'm going to take a look at this population. The prevalence, the percentage of people in the population that have this allergy is equal to 20%, 0.20 or 20%. Okay, so now I'm going to look at a diagnostic test for nickel allergies. Okay, and this is a pretty simple, inexpensive diagnostic test. It's kind of meant as a screening test. I'm going to draw a little box over here. And in this box, I'm going to put in, right? I'm going to put in on the rows, I'm going to put in whether a person has a positive test or a negative test for nickel sensitivity in this test. And up here, I'm going to put disease, positive, that these are people in this column that have that are allergic to nickel, and disease, negative, people in this column don't have allergies to nickel. So I'm going to put diagnostic test plus, diagnostic test negative, and in this box, I'm going to put all my outcomes. So now let's say I'm looking at a population of 1,000 people, right? Well, the sum here, right? If it's 20% prevalence, how many people out of that population do we expect to have a nickel allergy, right? 1,000 people, 20% of 1,000 people is how many? Anybody want to hazard a guess? If the prevalence is 20%, and we look at 1,000 people, it's going to be 200 people. Thank you. Okay, how many people not going to have the allergies? It's going to be 800 people. 200 have the condition, 800 don't have the condition. Well, now I'm going to tell you something special about this test. I'm going to tell you that this test is 80% effective at identifying people who have the condition. Okay, that has a special name. That's called the specificity. Okay, the specificity is 80%. In other words, these 200 people, if we screen them with the test, we will get that right 80% of the time. So if we have 200 people that have the disease, 80% of that is 160 people. We'll get it right for 160 people. We'll get it wrong for 40 people out of that 200. Right? We're only looking at people that have the disease. That's called specificity. Okay, so now let me ask you this. Let's see, it's 160 and 20. What's a good name for a person that has the disease, has the condition, and I'm going to put T plus and T minus, right, rather than diagnostic, that tests positive, that also has the disease. What's a good name for that? Anybody have a good name for that? Okay, well, hang on. I'll get to that, Alexa. People who have the disease sensitivity. Actually, the people at the sensitivity is the percentage of the time that you correctly identify people that have the disease. So we're right with these people that have the disease. We're right 80% of the time out of these 200 people that have the disease. So we only get it right 160 out of 200 people. 40 people test negatively. So what can we call this right here? We're going to call these 160 people. That's a good guess. Positive prevalence. It's positive, but I'm going to call those true positives. TP. True positives. Okay. Now these people tested false. These people tested negative, but they have the disease. So what kind of negatives would we call that? Okay. Let's call that. It's not a false positive. It's actually, remember, they tested negative, right? So it's a false negative, right? These tested negative, people tested negative, but they actually have the disease. They're in the column of people who have the disease. Okay, so now I'm going to give you another parameter. I'm going to call that 90% I'm sorry, who just said sensitivity? Okay, I didn't even realize I wrote that. Sensitivity, right? This is the sensitivity of the test, is the probability that you're going to get it right. Okay, okay, Alexa, you're right. Okay, the specificity of the test is how good you are at identifying people that don't have the disease. So we're 90% of the time we're right at identifying people that don't have the disease. Well, in other words, we should get a negative test for these people that don't have the disease. In other words, people in here. So if we're not right 90% of the time out of 800 people that don't have the disease, well, we should be right 720 times out of that 800 people. 80 times, 10% of the time, we're going to be wrong. So this is a true negative. They don't have the disease and they tested negative. And this is going to be our false positive, right? They tested positive, but they don't have the disease. Okay, so this tells us a lot about this test. This box gives us a very interesting view of how this test works. The specificity is 80% and the sensitivity is 90%. Now, I'm going to calculate another number. I'm going to calculate something called the PPV, or in other words, positive predictive value. Okay, I'm gonna add these up going across. Let's see, how many people tested positive out of these 1,000 people and randomly chosen in the population? 160 and 80. We had 240 people test positive, right? Out of those 240 people that tested positive, how many of them actually had the disease? Somebody want to tell me? How many people out of those 240, how many actually had the disease? 160, right? So if I put that 160 over 240, what does it tell me? It tells me that 2 out of 3, or 67% of the time, if you test positive, you have the disease. Well, what does that mean to me? That means that if I go to the doctor and he gives me this test, right, this is only going to be right 67% of the time. Okay, you guys, okay, you got that? We're right 67% of the time. Let me try and get this to move over. Good. So I can see. That's a positive predictive value. That's pretty interesting. Actually, that's not bad. This is a screening test. This is an inexpensive, quick test that a doctor might use to screen patients. A lot of diabetic tests, like taking a quick blood sugar or something like that, is this kind of diagnostic test. It has a certain positive predictive value. It has a certain sensitivity. It has a certain specificity. You can actually look up for diagnostic tests what studies show is the specificity or sensitivity. And for a lot of tests, 80% is not bad, for sensitivity. And 90% for specificity is not terrible either. We'd want it to be better, but for a screening test, this is not so bad. Now, the prevalence of this condition, that's pretty high. 20% of the people have any kind of condition. That's a pretty high prevalence. I'm going to take another look at this. Let's say that we're looking at another population where the prevalence is 1%, okay, of the condition. Let's say it's a different kind. We'll use nickel again. Let's say we're going to apply the same test to a population where the prevalence of this condition is 1% of the population has it. So I'm going to take 1,000 people again. Okay, here's disease positive, disease negative, test positive, test negative. Okay, I'm going to say I got 1,000 people who I surveyed in this population. Okay, so if the prevalence is 1%, what percentage of that 1,000 people, what number of thousand out of 1,000 people would we expect to have this disease, right? What's 1% of 1,000? Opinion? 10. Only 10 people out of 1,000 are going to have this disease in this population. That leaves 990 people that don't have this condition. All right, fair enough. But I said the sensitivity, I got it right this time, okay? Thank you, Alexa, is equal to 80%. And the specificity is equal to 90%. Same test, we're just applying it to a different population. Okay, so let's take a look and see what happens here. We're right 80% of the time in terms of this positive diagnostic test, right? So let's see. I got 10 people that actually have the disease. I'm right at identifying them 80% of the time. So I get that right 8 times. I get it wrong twice. So my true positives are 8. My false negatives, the people that I miss, are 2. Okay, so now let's take a look at the 900 people that don't have this disease. Again, this is the same sensitivity and specificity. 90% of the time, we correctly identify that they don't have the disease, right? So 90% of 990, well, I'm going to actually 990, I'm going to take 10% of that is 99. So I get it wrong 99% of the time. I get it right 901 times out of that 990. Did I get that right? That looks right to me, right? Okay, adds up to, 801. No, I got it right, 901, right? 99 times I predict that a person has that nickel allergy because 10% of the time I'm going to be wrong. 90% of the time I'll be right. 10% of the time out of 990, I'm going to be wrong. Everybody with me so far? 889. Oh yeah, 99 minus 9, yeah, 890 is 91. 891. Don't give me so many opinions. 891. Okay, that's good. Okay, I'm right with the 99. That's the part where I was more concerned about, actually. I'm right with the 99. Now let's calculate our positive predictive value. A positive predictive value is going to be the number of true positives, the 8 people that actually have the disease and we get correct, and over the total number of positives that we get in this population. Well, that happens to be 107. So 8 out of 107, our positive predictive value is only roughly, I don't know, I'm going to say 7%. So wow, that's a problem. If you go to the doctor, you get tested for nickel allergy, there's only a 7% chance you actually have it. Why did this change? Why did the positive predictive value change so drastically? What's the one thing that we changed in this population? We didn't change the test. We didn't change the sensitivity. We didn't change the specificity. What did we change? We changed the prevalence. When you have a disease that has a very low prevalence, right? If you have any kind of like weakness in your sensitivity or specificity, it's amplified by how much of the population doesn't have the disease that you wind up testing. So positive predictive value for many diagnostic tests goes way down when it's a low prevalence disease in the population. Can you guys give me an example of diseases that you know that they screen for, that there's a lot of controversy about because they have such a poor predictive value, and you wind up getting a lot of false positives and wind up with a poor predictive value? Okay, breast cancer, exactly right. Not so much HIV, because HIV, the tests that they used to use screening tests that were fairly weak, and they had a relatively high, a relatively bad positive predictive value with the screening tests. But now they're using much more sophisticated tests, so the specificity is really, really high. So you don't get very many false positives with those tests anymore. What's Tay-Sachs? Tay-Sachs, is that a genetic disease? HPV, I don't know. I don't know what the prevalence for HPV is pretty high, right? Human papillomavirus, the prevalence is pretty high in the population. So I'm not so sure that that's a good example. But how about pap smears, right? They encourage women to take pap smears, and yet the positive predictive value is very poor. The prevalence of actual uterine cancer or cancers that are detected by a pap smear, the prevalence is relatively low relative to the senioritis. Yeah, is relatively low compared to the size of the population that they're checking. Okay, that's a good question. I'm not sure about some of the others. I know, for instance, the PSA test for prostate cancer. Exactly. That's got a lot of that has a lot of controversy attached to it for the same reason. They screen everybody over a certain age, all males over a certain age, for prostate cancer, and it's not the specificity is not great, and the prevalence at the age where they start screening is not very high. Of course, males as you get older and older, like I probably 80% of males, eventually, if they live long enough, will develop some form of prostate cancer of one kind or another, usually somewhat innocuous versions of it. But when they're in that 40, 50-year age range where they start screening, the prevalence is relatively low and the specificity is not great. So they wind up with a lot of false positives, right? So now the one other thing I wanted to point out about this test, positive predictive value. What are we looking at in positive predictive value? We're looking at the probability that a person has the disease given that they what? You finish that sentence for me. Positive predictive value is the probability that a person actually has the disease given that they, somebody complete the sentence, test positive. Exactly. What kind of probability is that? It's a conditional probability, just like we were looking at with that table. If you're male, what's the probability? If you're given that you're male, what's the probability you're divorced? And so on and so forth would be a conditional probability. Or given that you're over 50 years old, what's the probability you're also over 70 in this population? Conditional probability. Positive predictive value is a conditional probability. You're looking at all the people that your condition is that we're only going to look at the people that test positive. That's where that 107 came from. And the probability that you actually have the disease is 8 out of that 107, our conditional probability. I'll give you another conditional probability. What's the negative predictive value, okay, for this particular population? Well, let me see. In this case, we're looking at only the people that test negative. How many people test negative? 2, and this was 891 after I finally got it straight. So that's 893 people, right? That's going to be over 893 people, right? And the number of people that tested negative that are indeed, the number of people that are negative out of that 893 is 891. So the probability that you're negative if you test negative is 99 plus percent, right? So that's a very good prediction rate. But the problem is that when you test a large population and the prevalence is very low, even if the sensitivity is decent, you're going to wind up getting a lot of false positives, sometimes more false positives than real positives in this kind of situation. So that's what we're talking about when we look at diagnostic tests. Okay, it involves some probability, particularly we're interested in conditional probabilities here. Okay, but that's an important measure, the sensitivity, the specificity, and especially the positive and negative predictive value, are very important measures on how valuable a diagnostic test is.